Okay, so my talk will be dealing with the way you can assess braking loads on offshore wind turbines through two different approaches. The first one is through the engineering approach that you can apply to assess the braking loads. And the second topic of the talk will be a discussion on how you can capture this kind of loads and the important information to assess the load at sea. This will be the two topics today. So I will repeat what I said as an introduction. So the main objectives of the project is to reduce the uncertainties in the design of offshore renewable energy converters regarding slamming loads. As you could see just before, we are actually working the project not only on the slamming loads itself, but also on the steps that are required to estimate the slamming loads, meaning defining the proper extreme state climatology, defining where you should put your, for instance, offshore wind turbine to avoid areas of high waves, as demonstrated by Matthias. And again, I would like to stress that slamming loads are very specific loads that can be the design load for especially offshore wind turbines. These are basically the slams that you can feel when you swim or when you go to swim on a beach exposed to large waves, large breaking waves. Okay, so on this slide, you see an extreme example of slamming waves on the lighthouse. So you can see a very large wave. It's about 20 meters high. That is basically behaving like a wall of water. And you have a sketch in the middle that show you the parameter of interest here. So here the cylinder could be the lighthouse, or it could be, for instance, a floating offshore, an offshore wind turbine. The wave is represented here on the left. The parameter of interest are the height of the wave, the elevation of the crest, eta b, the speed of the crest itself, that is supposed to be the same as the field velocity in the part of the crest which is vertical. And the other parameter of interest is the lambda parameter that gives you the portion or the proportion of the crest that is vertical. And this is exactly where the slamming load applies, where you have a portion of the crest that is parallel to the structure here. In the middle of the slide here, you can also see the engineering formula that was proposed by Godin in 1966 that gives you a way to compute the slamming loads on the cylinder, and therefore, for instance, on the mass of a floating wind turbine or bottom fixed wind turbine with a different parameter of interest. So we will be discussing two main questions today. First, the first question is, what is the sensitivity of the slamming loads to the wave approach that you choose to compute the parameter of interest, meaning the curling factor lambda, the crest elevation eta b, and the phase velocity here. So of course, sorry, I forgot to tell you, but rho is the water density, r is the radius of the cylinder here, and t is the time. So it gives you the evolution in time of this slamming force on the cylinder due to this kind of wave. So first question, what is the sensitivity of slamming loads to the wave approach chosen? So what do we mean by wave approach? So basically, to compute the parameter of interest, c, which is speed of the crest, lambda, the curling factor, eta b, the elevation of the crest. The classical engineering approach, which is the fastest one, is to use a stream function theory that allows you to simulate steep waves that are symmetric and regular. And as you will see, the fact that they are symmetric is the main limitation when you want to reproduce the impact of breaking waves that is generally quite asymmetric with a front face that is much steeper than the back face here. And this is the main reason why you have a slamming load. So we'll be discussing that now. So there are other approaches that are more complicated to represent a breaking wave, and I will show you an example that was done using Greely's model, that is a fully nonlinear potential model that was run during the PhD thesis of Audrey Varin that was done in the frame of the DIME project. And as you will see, it will enable you to generate waves that are breaking and that are asymmetric. So here it's a shallow water breaking waves over a slope. And as you can see here, you can see that the shape of the waves is very asymmetric. There is very steep front, vertical front here, and a much milder slope on the back. And what you can see also is that the distribution of the fluid velocity that is given by the color bar here is asymmetric as well, with a concentration of high velocities where the front is vertical, that you cannot capture neither with the stream function approach. Okay, so we will use this model to compute the parameter of interest of the equation above, and we will see whether with the engineering approach that uses stream function theory, we will achieve the same results in terms of timing loads or not. So here is the case study. So this is a work that was performed by Marc Prévosto at Ifremer, who is now retired. So what you can see here is a simulation of a wave that is passing through 3 offshore wind masts of foundation here, which is not, the spacing between the masts is not realistic, but the idea is to study the evolution of the loads depending of the relative location of the mast regarding the waves. So the solid lines show the waves at breaking onset, where you have a vertical front, and the 2 other dashed line shows the wave just before it breaks, so where the front is not vertical yet. Okay, so we'll be comparing the load at the 3 locations. So the hypothesis is a bottom fixed turbine on the slope bottom that we cannot see here, but that explains the shape of the waves. It's a 2D wave, and there is no fluid structure interaction accounting here. So the wave is passing through the foundation without feeding them. Okay, and we are just collecting the relevant information to compute this formula. So first we will be comparing the shape of the 2 waves that we are considering. So the first one is is following the DNV recommendation. So it's a nonlinear regular symmetric wave on a flat seabed, which is shown in red. You can see here that you have this peak shape, which is symmetric, front face and back face. And the blue line is the asymmetric solution that we show. There is a confusion for the colors, but the blue line is indeed the red line on the previous slide. Okay, previous figure here. So the blue line is the asymmetric wave that we simulate with the fully nonlinear potential model. So what you can see, of course, is that the shape is quite different as expected. So basically, the trough of the asymmetric wave, the front trough is deeper, and especially the slope of the front face is different. So it's steeper for the asymmetric solution from the fully nonlinear potential model, and it's symmetric for the solution given by the stream function-like theory. And this has important implication on the loads, as we will discuss now. So we will be first comparing the loads for this nonlinear asymmetric wave. So for the first mask, what you can see, if you look at the total load, which is in blue, and the decomposition into the Morrison load, which is the load induced by a wave that is non-breaking on the mass, and the impact additional load, that is basically the slamming load that I showed with the formula from Godard, which is in red here, is that when the wave is not breaking, the total load is dominated by the Morrison load, as expected. So if you go one step further, you see that Morrison is still dominating, but impact is starting to pick up a bit. But when you look at the third step, when the wave is at breaking onset, when it reaches the foundation of the offshore wind turbine. Here you can see that the load is dominated by the impact load that is much higher than the motion load here for this specific instance. Okay. So slamming loads become dominant when a vertical front is present. So now if we compare the loads induced by the asymmetric wave and the symmetric one, what you can see here, so the load induced by the asymmetric one is given by the solid lines at breaking onset, and the one given by the symmetric wave, which is the recommendation from the certification document, is given by the dashed line. And what you can see here is that the peak loads are underestimated if you use the symmetric one, and especially this is due because the slope is not so vertical, and the loads are not so impulsive and not so high compared to the solution given by the more realistic asymmetric solution from the fully nonlinear potential model that is used. So the first conclusion for this first part of my presentation is that the slamming loads dominate the load if a vertical wavefront is present. So in this situation, if you apply the stream function theory, you will have an underestimation of the peak load. So it is recommended to apply numerical approaches that are able to capture the crest, the wave crest asymmetry, and the presence of a vertical front. Okay. So I'm just repeating what I just said. So second question is how we can capture this information of interest in the field. So it means you need to know the properties of the wave in terms of crest elevations, the field or the crest velocity c, and of course the presence or not of a vertical front, which is characterized by the curling factors that I presented in the equation at the beginning of the talk. So for this, we designed an experiment on a lighthouse. So you may wonder why we are working on a lighthouse while we are interested in floating or float and fixed offshore wind turbine. It's because we are using this as a lab or a demonstrator for an experiment that we will be deploying very soon, hopefully, on the former Hywind demo floating offshore wind turbine deployed in Norway in the frame of the DIMPACT project. So the experiment is made of a stereo system that enables you to reconstruct the sea surface and the wave shape in space anytime, as I will show. We have also pressure sensors that are able to record the pressure loads due to the slamming waves, and accelerometers that enables you to track the displacements and the motion of the structure due to the impact. So why did we pick Lagimon Lighthouse? It's quite obvious. I will show you. So it is exposed to extreme waves. This one is about 20 meters high. Of course, this is here bottom induced, but what is nice as well is that if you can also look at waves that are further offshore, because the water depth is very quickly dropping to 80 meters. And we are actually doing both action at the lighthouse. But here we will be focusing on the near field waves, which are in shallow water. Okay, so it's a very famous lighthouse. There is one picture with a lighthouse keeper standing here while there is a big breaking waves around the lighthouse that is known worldwide, I guess. So as you guess, it's a very wide environment, and it's very hard to access it. So we had to access it through helicopter during the first winter, which is quite an experience, of course. This is my boots that you can actually see on the video here. Okay, and so just to quickly explain you why this kind of measurement protocol is so useful to understand the braking and the slamming loads on the offshore structure. I will show you an example of the exploitation of our dataset. That is exploiting one event, and we will be conducting a sort of response-based design approach here. So we actually looked at the acceleration here in time that is measured at the top of the lighthouse on January the 3rd, 2018, between 9:42 and 10:08 a.m. And what you can see is that there is a very strong acceleration of the top of the tower that resulted in a displacement of about 5 millimeters of the top of the lighthouse during this record. That is much higher than the other acceleration felt by the lighthouse induced by the waves. So if you look at the corresponding wave that we capture with the stereo imaging, you can see that it is quite high. The crest elevation is about 13 meters high, but it's not much higher than a few other events that didn't cause any extreme acceleration of the top. So we tried to understand why this wave was so severe and why it shook the lighthouse so badly. So this wave is this one. It's a wave 1 that we call it wave 1. It's a giant wave, 19 meters high from crest from trough to crest. Crest elevation 13 meters, and as you can see, it sprays water up to the top of the lighthouse. So it's similar condition as the one that you can see here that we recorded. So it's not the same time, but it's a similar wave impact that we recorded here. And so our investigation drove us to conclude that actually the reason why this wave shook the lighthouse so badly was because the crest elevation was higher than the substructure that was added after the construction to make the lighthouse stiffer. And so the crest actually reached the tower that is much more flexible than the substructure here, and this is why this wave in particular caused the lighthouse to shake so bad. So we demonstrated that this was a very interesting protocol to study extreme loads on offshore structure, and we are replicating the same experimental protocol on the floating offshore wind turbine named now Zephyros, but which is the former Hywind demo in Norway. We are waiting for a weather window to implement the exact same instrument on the platform. Okay, and so it's part of the DIMPACT project that shares some partners with the DIME project, and that is focusing on the slamming loads on floating offshore wind turbines. So it started in May 2020, and it's currently running.